Hello everyone. Today I'm going to present our work, Mask Point, Masked Discrimination for Self-Supervised Learning on Point Clouds. This work is done jointly by Haotian, Mu, and Yangjae. Comparing to the labeling cost of 2D tasks, labeling 3D scenes requires much more effort, as there are more dimensionality of the object property to label. Therefore, it will be of much benefit if self-supervised learning can be used in point cloud, as it can not only reduce the labeling cost, but also improve the model's performance. Masked modeling has been successful in self-supervised learning in natural language processing. Recently, PointBird adopts its idea to point clouds. First, it trains a DGCN network as a tokenizer that can represent the input point cloud with a set of discrete tokens. Then it masks out a portion of the point embeddings, feeds them into the encoder, and trains it to repredict the generated discrete tokens. It improves the performance of standard transformers for point clouds while having two drawbacks. First, it needs to train a separate tokenizer beforehand, which can be quite costly. Second, the model's performance and transferability is limited by this tokenizer. For image understanding, masked autoencoders have shown great promise without the need of a separate tokenizer. The idea is simple and effective. It first masks a large portion of the image patches, feeds the visible patches into a transformer encoder, and then uses a transformer decoder to reconstruct the original image pixels. However, we cannot simply adopt its idea to point clouds. When all patches are fed into the decoder, they are bundled with the positional embeddings. From the positional embeddings, the model can roughly tell what the original point cloud looks like. For example, here, the model can see a blurred plane shape, which leaks the information for the reconstruction. This makes the pre-training task much easier and can result in suboptimal pre-training. To solve this problem, we propose to not only feed the unmasked point clouds, but also randomly sample some noisy patches to feed into the decoder. Instead of using a generative task, we train the model to classify the input points as real or fake. To this end, we propose Mask Point with our novel mask discriminative pre-training objective. First, we partition the point clouds into two groups, masked and unmasked. We feed the unmasked point groups to the transformer encoder. Then, we generate two sets of the queries, real ones from the masked point clouds and fake ones that are randomly sampled from the 3D space. We train the transformer decoder so that it can classify the input queries as real or fake. This objective creates a pretext task that is difficult and meaningful enough for the model to learn rich semantic point cloud representations. For the results, we first compare our model with the baselines on 3D object classification tasks. On ModelNet 40, Mask Point improves the train from scratch baseline by a significant 2.5% points. It also improves over the PointBird baseline by 0.6%. Notably, for the first time, a standard transformer architecture outperforms the sophisticatedly designed 3D point cloud networks like Point Transformer. On the challenging scan object and dataset, Mask Point achieves a state-of-the-art performance, improving over the baselines by a significant 1.2% to 7.1% points.
Furthermore, we are the first one to evaluate masked point cloud modeling on the challenging real-world object detection task. For ScanNet 3D object detection, PointBird even shows worse performance than trained from square result in AP25. However, after pre-training on 10% of the raw ScanNet dataset, we achieved significant improvements on both AP25 and AP50. Besides, our model can reconstruct the objects by sampling the points from the scene. After dropping the negative points out of the binary classification results, we can achieve this functionality. As you can see, we can reconstruct things like chairs, airplanes, and desks quite well. Besides, our model can even complete the missing points in the original scene, such as the right corner of the desk surface, demonstrating that our model has a deep understanding of the scene.
In summary, we propose Mask Point, a novel discriminative mask transformer framework for point clouds. Its learned representations has been transferring very well to new tasks and domains. Mask Point has also achieved state-of-the-art on various downstream tasks. Please check out our paper by scanning the QR code, and our codes and models are publicly available on GitHub.